Version 6 of Montage includes Python binary extensions of 38 Montage modules, which allows you to run Montage at compile speeds in a Python environment. I'm Bruce Berriman, and I'm going to show you how you can use Montage operating in a Python environment to create an image mosaic. I'm using Python 3.6 for this demonstration, but any version above Python 2.7 will in fact work just fine. The notebook I'm using here is available for download at the Montage GitHub page. You can also find demonstration notebooks for each of the Montage modules in the same repository. So we are going to create a 1 degree by 1 degree mosaic of M17 in the 2-mass J-band. To begin, we simply import Montage along with 2 or 3 other modules that we need to run the script. Setting up the working environment essentially involves creating several directories which will hold the images that have been processed in various stages of the workflow. After that, we create the fits header for the mosaic by calling the mHeader routine, and then we go ahead and retrieve the archive images. Now to do this, we use the mDownload utility, which is included in the Montage distribution. It provides access to a number of wide area sky surveys, 2mass, WISE, Sloan, SDSS, and DSS. You can use your favorite data access service, of course, as you wish. Once you have the data downloaded, you create a table of the metadata of all the raw images that you've downloaded, and these are stored in an IPAC column delimited ASCII table. Now the returns here show you that each of these stages has been successful and that we have downloaded a total of 49 images that we're going to mosaic together. Now we can actually do the reprojection and create the mosaics. First stage is to reproject the original images to the frame of the output fits header that we've just created. Now generally this is the most compute intensive part of the whole process. We're using spherical geometry to perform the reprojection. Now this is the most general method available, but it can also be quite slow sometimes. To speed things up under certain circumstances, we've actually created 2 more reprojection modules. mProject.pp allows you to perform a plane-to-plane rather than spherical geometry reprojection for tangent plane projections only, which are actually very common in astronomy. mProject.ql is much more general. It uses image interpolation techniques and it will reproject any projection that is supported by WCS. Both of these modules offer a factor of 20 speed up over the spherical geometry method, but they do have their limitations. Once the reprojection has been done, we create another metadata table for all the reprojected images. The returns here show you that each of these 2 steps have been completed successfully. Now we can actually create the mosaic by simply co-adding all the reprojected images. And we can view the image with MViewer. MViewer uses an adaptive stretch algorithm to create a PNG representation of a FITS file. Many astronomical images contain a pseudo-Gaussian distribution of brightness at the lowest levels and a long tail of brighter sources attached onto it. MViewer uses a histogram equalization technique to create a PNG representation that is a balance between, on the one hand, the low-level structure of the image, and on the other hand, the structure and variations of the brighter sources. So this is our image mosaic. Now the vertical stripes that you see here represent variations in the sky background levels from image to image, which all have been acquired at different times. Now there's no physical model that we can use to correct the mosaic for these background variations. So Montage takes the approach, which as far as I know is unique to it, of calculating the set of minimum adjustments needed to bring the image backgrounds into line with each other. and these are the steps that we then carry out next. Right, we calculate the overlap areas between the various pairs of images, and once we've done that, we actually compute the differences in flux between them, and then fit them with a plane. And then finally, we use all these fits to determine iteratively a global minimum difference model, which gives us corrections that will apply to each of the images. Well, having successfully computed the background model, we can then go and apply it to the individual images. Again, we create another metadata table, and then we can compute our final co-added image. And again, we will look at it with MViewer. And this is the final image, and you can see that it has the background levels have been rectified to a common level across all the images. So this is the end of this demonstration. I hope it's been instructive, and happy image processing. Thank you for listening.